Hello. I hope you guys are doing well. Welcome to another session of Bed Talks, TED Talks from my bedroom. I hope that you're doing well and getting ready back to school and all that, and everybody's staying healthy and all that. Today, what I'm going to tackle in this little bit of a section is sections 14.1, and that's going to cover multivariable functions, domain, and contour plots of different types of multivariable functions. So the first thing we need to think about is, why would we need multivariable functions? Well, just as a reminder, the idea of a function, if I had something like this, f of x equals x squared minus 4, this tells me I have one input. This function f has one input, and I get one output, right? So I have one variable that's dependent on this. And kind of thinking about what this means, right? If I plug in an x, let's say I plug in x equal to 2, and I plug this in, I get f of 2. If you can see here, this will become 0. So that means on my graph, I have a point 2, 0. I can do this for every single one, right? I can give you an x, I can tell you my y value, I can tell you my height. That's kind of the idea. So if I extend this, now if I have two variables, x and y, let's say equal to maybe something like that, x minus y plus 3. What this tells me is I plug in two inputs. I have two inputs. I plug in two things, and then I get one output. So let's say, for instance, I plug in 2, 3. If I plug this in, I get 2 minus 3 plus 3, and this gives me 2. Now, what does this tell me? This tells me that 2, 3, I plug in 2 and 3, I get a height of 2. You can kind of imagine that I'm going to have a point on my graph of 2, 3, 2. So you can kind of imagine that in my xy plane, I pick the point 2, 3, maybe it's up there, and I go up a height of 2, and that's going to be on my graph. So this is kind of the idea of a multivariable function. I have multiple things depending on what the output's going to be. This is very, very real life, right? You got to think about, maybe, for instance, objects falling from the sky are dependent on a lot of things: gravity, drag. Even temperature could be dependent on. So a lot of different variables can come into play. And this allows us to kind of do that. We can extend this to as many variables as we would like. Now, one thing we like to check out is the idea of the domain. What values of, for instance, x or x and y will allow me to get an output, So if I was to tackle something like this, f of x equals the square root of x minus 2. Well, if I want to figure out the domain of this, I need to think about all the values of x that would produce an output. In this case, we see that, well, under a square root, I can't have negative numbers. So that means that x minus 2 must be greater than or equal to 0. And you could solve this to be x is greater than 2. So that's my domain. You could write this interval notation as thusly, right? 2 to infinity, including 2, right? Because 2, the square root of 0 is 0. So this tells me all the values. If I plug in -1, I can't get an answer. I can get an imaginary answer, but we're thinking about real answers here. So if I extend this now to 2 dimensions, what does that kind of entail, right? How do I do this? Well, let's take a look at maybe something like this. Y minus x divided by x plus 3. Something like that. Now, in this problem, I need to find all of my x and y such that I can produce an output. I can get an output here. Now, this is kind of an interesting one because there's a lot of different facets to it. We're going to have a region that's going to be, we have an xy plane, right? We're going to kind of think about this. We're going to have this xy plane here that's a region that I'm going to be able to plug in numbers into. Here, I have to think about the conditions that I have. I have a fraction and I have a square root. The first thing, as we kind of just did in the previous problem, is that my square root here, I can't have a negative under it. So I note here that, okay, y minus x has to be greater than or equal to 0. Move this over. It's a little bit nicer to say that y has to be greater than or equal to x. You kind of imagine, I'm going to draw this out in a little bit, but I'm going to have my line y equals x, and it's everything above that line. Now, the other thing I need to worry about is since I have a fraction here, I have x plus 3. I can't have a 0 in my denominator. So what I do is I take this x plus 3 and I need to find, when that's 0, right? And x plus 3 is 0 when x is equal to -3. And that's a vertical line at x equal -3. So if we plug in all these things together, this is my domain. I need x to be greater than or equal to x, y greater than or equal to x, and x can't be equal to -3. So to do this, I draw the line. I think it's easiest to draw the line y equals x. So there's this equality here. So let's try the line y equals x, like that. Okay, and this tells me and going everything above that. So you can kind of just plug in a point. I would suggest doing plug in a point to make sure that's kind of the region where to go. So here, for instance, I plug in, maybe 1, 0. As you can see, the point 1, 0 would satisfy this. So it's everything above this. And we have the solid line here. Be aware, we have a solid line, right? We have a solid line specifically when we have this equality. Now, the other thing I'm not including yet is this x not equal to -3. That means that anything on, well, if I plug in -3 here, I have to have this dotted line here. So to kind of be a little bit careful, what we usually do is we draw a dotted line like that to denote that we have kind of an area that can't be hit. So here's my -3 at this point, and I have this line. So this is my region of my region that I can find the domain of this function. It's everything above this line except on the line x equal to -3, and that's my domain. We usually don't use interval notation here. It's usually very difficult to, and because of that, we usually just draw it out. So this is kind of the process you would do, and many times you have to kind of remember some interesting things about functions. For instance, the argument of a log has to be greater than 0, strictly greater than 0. Nothing under denominators, and usually the square root functions. Usually those are the issues that usually come about. That's kind of how you do the domain. And so, last thing I want to tackle is the idea of level curves. And it's actually kind of funny. I have a picture here. My dad actually lives in Colorado, and we go hiking pretty frequently whenever I go out there. He's a huge hiker of like 14ers, so 14,000 feet. And one of the first climbs I did with him out there with the 14er was a peak called Grays and Torreys. And I actually got this little poster here. Grays and Torreys, it's actually, so they're right next to each other. And you do them both at the same time. And there are 14,278 feet and 274 feet. Yeah, Grays is a little bit bigger. So I love hiking. And whenever we do hiking, we always have to check out the topographical graphs. And we have like those elevation profiles, those contour plots to kind of see maybe something like this. Right? Maybe you see something like, if I take a look, something, I'm kind of drawing a little bit like an egg at the moment. But you get these different topographical profiles. And what does this actually tell you? Right? This might tell you that this is at 100 feet, 120 feet, 140 feet, 160 feet, 180 feet, and 200 feet. What this tells you is that at every single one of these lines, 100, 200, 140, and all that, they're always at the same elevation. You kind of imagine that I'm taking a plane and I'm slicing through at a different height at sea level, slicing through and just seeing what that intersection of that slice and that curve is. Kind of think of it as a mountain, right? As a mountain, I take a slice of it, what happens? And this is what happens. I take these slices. And it allows us to kind of see, as you can see here, this kind of shows you, oh, I'm going to have probably a peak up at this point because I have more and more, I have higher and higher elevation profiles. So how do I find these, right? How do I find these level curves? What do these level curves start to look like? And so on, right? Sometimes they have some very interesting level curves. So let me just define what a level curve is. A level curve is when f of xy is equal to some number k, where k is some number. Is a number. So for instance, k could be any elevation profile. For instance, 114,278, for instance, or 100, or sea level 0, or negative 100. This will give us some surface on the xy plane and some curve on the xy plane that shows me the intersection. So what I want to do here now is let me show you an example of how to find these level curves and what they start to look like. So let's take a look at something like, oh, I don't know, maybe like x times y. Something like that. F of xy equals xy. Now, what are the level curves of this? Let's say we want to find the level curves at xk equals 0, -1 and 2. That seems pretty reasonable. So what we do to do this, I'm going to have my little graph over here, x, y. And we're going to start off with k0, -1 and 2. I want to find out what coordinates x, y give me a k to be 0. So the first thing I'm going to do, k is 0. I get 0 is equal to x times y. So when does this happen? Well, I hope you'd agree here that this either happens when x is equal to 0 or when y is equal to 0. And those are the axes. So I like to draw this out. And you want to be very careful when you're doing this, because many times what we're going to want to do is we want to say like, this is k to be 0, k to be 0. You want to make sure you're labeling your graphs. If you don't label your graphs, it's really tough to tell kind of what height profiles they are. And maybe there's some really interesting ones that are maybe more discontinuous. And you want to just make sure as best as you can. So here we see that if 0 is equal to x, y, you know, either x has to be 0 or y has to be 0. That's pretty nice. So this means that at this entire axis right here, I'm always going to be at sea level. Let's try k equal to -1. When am I just below the xy plane? Well, I get something like this. You know, -1 is equal to x times y. I think it's a little bit easier if I move over the x. And I get y is equal to -1 over x. And you can kind of imagine, well, what does this look like? Well, this is kind of looking like, you know, one of those, you know, inverse functions, but this is a -1, so I kind of have to flip everything. Everything kind of has to get flipped. So I kind of get stuff like this, right? Get something like that. I probably should move this k over 0, go here. Something like that. And this is at, you know, -1, 1, and this is at, you know, 1, -1. We ought to just be careful there. I just make sure we at least have some semblance of what we're doing. And so this is at k equal to -1. So the entire time, if I stay on this entire contour at the moment, if I stay on this level curve, right, I'm always going to be at the same height. I'm never going to move height. Right? That's kind of the goal here. It's going to be important for us to go forward when we talk about something called the gradient. It's going to be really interesting to see the difference between, you know, the gradient contour lines and vector fields coming forward. But that's kind of a little bit like a, you know, that's something we'll talk about in the future. And lastly here, you kind of see that if I do k equal to 2, in the same way, I'm going to get y is equal to x, 2 over x. Okay. And again, you know, I get something very similar, but in this case, I'm on the other way. I'm on the way that we usually like to go. Something like that, right? And this is k is equal to 2, and k is equal to 2. If I do this very generally, you could probably see that if I do k equals xy, I would get y equals k over x. I'm always going to get these, you know, these types of features right here. So this tells us something actually really interesting. This tells us that as I move away, at least in this direction, I'm going to be gaining height, right? Because if k is like 10 or so, it's going to be over here. So I'm going to be gaining height as I go forward. I'm going to be losing height as I go down in these angles. It's kind of a very weird function. You're going to see it's actually a really, really interesting one. And semi-discontinuous, I think in some ways, but because of this like k over x kind of deal. But this kind of needed the elevation profile. This gives us some nice, interesting information. And, you know, this kind of leads us into thinking about how do we graph these things. I think that's a really, really interesting thing to do. You know, how do we graph these things? Usually what we're going to want to do is relate things like this to the quadratic surfaces that we've seen in the past, like cones or cylinders. Many times you kind of imagine this as the z component, and that's what you should kind of do. So for instance, you know, as an example, you know, if you have something like f of xy equals the square root of 9 minus x squared minus y squared, you know, like, what the heck is this? If you're asked to graph this, like, what is it? Right? You don't really know what it is. So what I would suggest doing, if I'm trying to figure this out, I let z, it's the same exact thing, right? My z, I'm thinking about this, this is my height, right? This is my height, so I can think about it that way. If I do this, I square both sides, I get z squared is equal to 9 minus x squared minus y squared. And then lastly here, I move this over, and I get this guy, x squared plus y squared plus z squared is 9. And you kind of see that this is probably a sphere of radius 3. And you have to be kind of careful. It's not a full sphere of radius 3, because I have this as a square root up here, 9 minus x squared minus y squared. So if you'd agree, I can't have a negative number out of this because it's not like a plus or minus. So it's just the top half of the sphere. So if I wanted to draw this out very poorly, you know, something like that. And it's just the outside. It's not the inside. It's just the shell of that. And that's kind of the idea. So if you're ever having issues with trying to do this, maybe if you're trying to plot something, it might be a little bit easier to kind of think about this as z. See if you can finagle the relationships around a little bit and get something nice. Okay, I will stop there. But if you have any questions, let me know. You know, post on Piazza or even on the comments below if you want to. And yeah, I hope you guys are doing well. It's 10:30 in the morning, but I hope that you're going well, and I will see you guys this week. Have a good one.